US Physics Olympiad year 2014 USA PHO exam. For whole contest that were given 6 problems, part A 4 problems, 90 minutes, and part B after a break another 90 minutes for 2 problems. All solutions for all 6 problems you can find below this video in the reference of the description. Problem A1. A unicyclist of total height h goes around circular track of radius r while leaning inward at an angle theta to the vertical. The acceleration due to gravity is g. Question A. Suppose that h much less than r. What angular velocity omega must the unicyclist sustain? Question B. Now model the unicyclist as a uniform rod of length h, where h is less than r, but not neglectable. This refined model introduces a correction to the previous result. What is the new expression for the angular velocity omega? Assume that the rod remains in the plane formed by the vertical and the radial directions, and that r is measured from the center of the circle to the point of contact at the ground. US Physics Olympiad year 2014 USA PHO. Final exam. Problem A2. A room air conditioner is modeled as a heat engine run in reverse. An amount of heat QL is absorbed from the room at a temperature TL into cooling coils containing a working gas. This gas is compressed adiabatically to a temperature TH. The gas is compressed isothermally in a coil outside the house, giving off an amount of heat QH. The gas expands adiabatically back to a temperature TL, and the cycle repeats. An amount of energy W is input into the system every cycle through an electric pump. This model describes the air conditioner with the best possible efficiency. Assume that the outside air temperature is TH and the inside air temperature is TL. The air conditioner unit consumes electric power P. Assume that the air is sufficiently dry so that no condensation of water occurs in the cooling coils of the air conditioner. Water boils at 373 kelvins and freezes at 273 kelvins at normal atmospheric pressure. Question A. Derive an expression for the maximum rate at which heat is removed from the room in terms of the air temperatures TH, TL, and the power consumed by the air conditioner P. Your derivation must refer to the entropy changes that occur in a Carnot cycle in order to receive full marks for this part. Question B. The room is insulated, but heat still passed into the room at a rate R equal K delta T, where delta T is the temperature difference between the inside and the outside of the room, and K is a constant. Find the coldest possible temperature of the room in terms of TH, K, and P. Question C. A typical room has a value of K equal 173 watt per degree Celsius If the outside temperature is 40 degrees Celsius, what minimum power should the air conditioner have to get the inside temperature down to 25 degrees Celsius? US Physics Olympiad, year 2014, USAPHO. Final exam. Problem A3. When studying problems in special relativity, it is often the invariant distance ds between two events that is most important, where ds is defined by this equation, where c equal 3 by 10 power 8 meters per second is the speed of light. Question A. Consider the motion of a projectile launched with the initial speed v0 at angle of theta 0 above the horizontal. Assume that g, the acceleration of free fall, is constant for the motion of the projectile. First, derive an expression for the invariant distance of the projectile as a function of time t as measured from the launch, assuming that it is launched at time t equals 0. Express your answer as a function of any or all of theta 0, v0, c, g, and t. Question 2. The radius of curvature of an object's trajectory can be estimated by assuming that the trajectory is a part of a circle. Determine the distance between the end points and measuring the maximum height above the straight line that connects the endpoints. Assuming that we mean invariant distance as defined above, find the radius of curvature of the projectile's trajectory as a function of any or all of theta 0, v0, c, g. Assume that the projectile lands at the same level from which it was launched, and assume that the motion is not relativistic, so v0 much less than c, and you can neglect terms with v over c compared to terms without. Part B. A rocket ship far from any gravitational mass is accelerating in the positive x direction at a constant rate g, as measured by someone inside the ship. Spaceman Fred, at the right end of the rocket, aims a laser pointer toward an alien at the left end of the rocket. The two are separated by a distance d, such that dg much less than c square. You can safely ignore terms of the form of this one. First question. Sketch a graph of the motion of both Fred and the alien on the space-time diagram provided in the answer sheet. The graph is not meant to be drawn to scale. Note that the t and x are reversed from a traditional graph. Assume that the rocket has velocity v equals 0 at time t0 and is located at position x equals 0. Clearly indicate any asymptotes and slopes of the asymptotes. Second question. If the frequency of the laser pointer as measured by Fred is f1, determine the frequency of the laser pointer as observed by the alien. It is reasonable to assume that f1 much greater than c over d. Question 2. If the frequency of the laser pointer as measured by Fred is f1, determine the frequency of the laser pointer as observed by the alien. It is reasonable to assume that f1 much greater than c over d. US Physics Olympiad, year 2014, USAPHO. Final round. Problem A4. A positive point charge Q is located inside a neutral hollow spherical conducting shell. The shell has inner radius A and outer radius B. A is not neglectable. The shell is centered on the origin. Part A. Assume that the point charge Q is located at the origin in the very center of the shell. First question. Determine the magnitude of the electric field outside the conducting shell at x equals b. Question 2. Sketch a graph for the magnitude of the electric field along the x-axis on the answer sheet provided. Question 3. Determine the electric potential at x equals a. Question 4. Sketch a graph for the electric potential along the x-axis on the answer sheet provided. Part B. Assume that the point charge Q is now located on the x-axis at the point x equals 2a/3. Question 1. Determine the magnitude of the electric field outside the conducting shell at x equals b. Question 2. Sketch a graph for the magnitude of the electric field along the x-axis on the answer sheet provided. Question 3. Determine the electric potential at x equals a. Question 4. Sketch a graph for the electric potential along the x-axis on the answer sheet provided. Question 5. Sketch a figure showing the electric field lines, if any, inside, within and outside the conducting shell on the answer sheet provided. You should show at least 8 field lines in any distinct region that has a non-zero field. US Physics Olympiad, year 2014, USAPHO. Final round. Problem B1. A block of mass big M has a hole drilled through it so that a ball of mass small m can either horizontally and then pass through the block and exit vertically upward. The ball and block are located on a frictionless surface. The block is originally at rest. Question A. Consider the scenario where the ball is traveling horizontally with a speed v0. The ball enters the block and is ejected out the top of the block. Assume there are no frictional losses as the ball passes through the block, and the ball rises to a height much higher than the dimensions of the block. The ball then returns to the level of the block, where it enters the top hole and then is ejected from the side hole. Determine the time t for the ball to return to the position where the original collision occurs, in terms of the mass ratio beta equal big M over small m, speed v0, and acceleration of free fall g. Question B. Now consider friction. The ball has a moment of inertia I equal 2/5 mr square and is originally not rotating. When it enters the hole in the block, it rubs against the surface so that when it is ejected upwards, the ball is rolling without slipping. To what height does the ball rise above the block? US Physics Olympiad, year 2014, USAPHO. Final exam. Problem B2. In parts A and B of this problem, assume that velocities v are much less than the speed of light c, and therefore ignore relativistic contraction of length or time dilation. Part A. An infinite uniform sheet has a surface charge density sigma and has infinitesimal thickness. The sheet lies in the xy plane. Question 1. Assuming the sheet is at rest, determine the electric field E, magnitude and direction above and below the sheet. Question 2. Assuming the sheet is moving with the velocity v in the direction x parallel to sheet, determine the electric field E, magnitude and direction above and below the sheet. Question 3. Assuming the sheet is moving with velocity v in x direction, determine the magnetic field B, magnitude and direction above and below the sheet. Question 4. Assuming the sheet is moving with velocity v in z direction perpendicular to the sheet, determine the electric field E, magnitude and direction above and below the sheet. Question 5. Assuming the sheet is moving with velocity v in z direction, determine the magnetic field B, magnitude and direction above and below the sheet. Part B. In a certain region there exists only the electric field E in form of Ex plus Ey plus Ez and no magnetic field, as measured by an observer at rest. The electric and magnetic fields E' and B' as measured by observers in motion can be determined entirely from the local value of E, regardless of the charge configuration that may have produced it. Question 1. What would be the observer electric field E as measured by an observer moving with velocity v in direction z? Question 2. What would be the observed magnetic field B as measured by an observer moving with the velocity v in direction z? Part C. An infinitely long wire on the z-axis is composed of positive charges with a linear charge density lambda, which are at rest, and negative charges with the linear charge density negative lambda, moving with the speed v in the z direction. Question 1. Determine the electric field E, magnitude and direction at points outside the wire. Question 2. Determine the magnetic field B, magnitude and direction at points outside the wire. Question 3. Now consider an observer moving with the speed v parallel to the z-axis, so that the negative charges appear to be at rest. There is a symmetry between the electric and magnetic fields, such that the variation to your answer to part B can be applied to the magnetic field in this part. You will need to change the multiplicative constant to something dimensionally correct and reverse the sign. Use this fact to find and describe the electric field measured by the moving observer, and comment on your result. Some familiarity with the special relativity can help you verify the direction of your result, but is not necessary to obtain the correct answer.